Hi, everybody. Today we have the pleasure of hearing from Dr. Umesh. He is an applied ecologist at the India Institute of Science. He's in India right now. He's going to be speaking for us today on climate change, forest degradation, and the future of Himalayan biodiversity. So thank you so much for coming. Thanks.
Thank you very much, and very good evening to all of you. What I want to talk to you about today is about some of the work that we've been doing in the eastern Himalayas of India for the last 11 or 12 years. And that's mostly to do with understanding how biodiversity responds to climate change and forest degradation, and what we can do to mitigate the impacts that these two threats pose to biodiversity in this region. This has been long-term work that's been going on for a long time, over a decade, and would not have been possible without funding from a number of sources, as well as institutional support from the Forest Department of India, as well as the Indian Institute of Science, and certainly would not have been possible without this exceptional crew of 6 people we have in the field, who are just absolutely great. The expert bird guides, expert mist netters, fantastic cooks, and without these folks in the field, all of the stuff that I'm going to be talking about would have been completely impossible. So shout out to all these institutions and these people for the work that we've been able to do. We know that we're living through the 6th ever mass extinction in Earth's history, one that's caused entirely by humanity and driven primarily by things like climate change and habitat loss. And what we do is we try and understand, we have 3 key research themes, try and understand how climate change might affect ecological communities, and how habitat loss and degradation affects the survival of species, and how climate change and habitat loss actually synergize to affect species. When it comes to climate change in ecological communities, we're concerned about temperature sensitivity and elevational ranges on mountains. How important is temperature in setting elevational ranges versus competition, for example? When it comes to habitat loss and degradation, we're looking at selective logging and the survival of Himalayan birds. How does selective logging alter survival rates in Himalayan birds? And finally, when it comes to interactions between climate change and habitat loss, we're asking, what does it take to survive in a warmer and more degraded Himalayan mountain range? So to begin with, temperature sensitivity and elevational ranges. Every species has a range, a geographical range, and every species obviously has geographical range limits. And the range limits is what define the range of the species. And look at two very closely related Australian species, the splendid and the super fairy wrens. The super fairy wren seems to be coastal species. It's found in habitats along the coast, whereas the splendid fairy wren is sort of a more inland species, or it's found along the west coast rather than along the east coast. And the question is, what is it that determines the range limits of these species? Is it competition? Does the super fairy wren prevent the splendid fairy wren from expanding eastwards? And does the splendid fairy wren prevent the super fairy wren from expanding westward? Or is it because the super fairy wren is simply adapted to coastal conditions, coastal abiotic conditions like the temperature and humidity along the coast, whereas the splendid fairy wren is more of a generalist species that can adapt to even inland drier conditions? Or is it a combination of the two? Is it a combination of the abiotic environment that species are adapted to, as well as competition between closely related species? And this is a question that is very, very old, a question that goes back to Darwin, in fact, who in his classical On the Origin of Species, Darwin said, look, the tropics have a large number of species. Tropics have a phenomenal number of species, whereas if you go towards the poles, the number of species reduces. So in the tropics, it should be competition between species that is setting range limits, whereas as you go polewards, the abiotic environment becomes much harsher, and therefore the temperature should be setting range limits as you go towards the poles and away from the equator. In 1967, Dan Jensen published a seminal paper in American Naturalist called Why Mountain Passes Are Higher in the Tropics. And Dan Jansen argued that it's actually temperature that sets range limits in the tropics, because the tropics are inherently less seasonal, and temperature variability within the annual cycle is very, very low. And therefore, species are adapted to be thermal specialists. And if they're adapted to be thermal specialists, then temperature should be very, very important in setting species range limits in the tropics, rather than towards the poles, where species are adapted to be thermal generalists, because they face very, very harsh winters and they face warm summers compared to what happens in the tropics. And so Dan Jansen actually overturned what Darwin was saying and said it's actually in the tropics that temperatures sets range limits. And we want to know to what extent temperature sets range limits, because that's going to have huge implications for climate change and how species adapt to climate change. This is especially concerning for the Himalayas, because the eastern Himalayas are warming 3 times as fast as the global average. And the Himalayas are exceptionally biodiverse. So if you look at a map of bird species richness color-coded across the world, the darker the color, the higher the number of bird species. You'll see that basically where you have the highest bird species richness, and this is true, of course, for all taxonomic groups, plants, mammals, arthropods, invertebrates, and so on. The maximum species richness is in terrestrial mountains, the Andes, the Eastern Arc Mountains of Africa, and the Himalayas. And these places are warming very, very fast. We know that species are shifting their ranges upwards to cope with climate change. And even though mountains cover only 25% of land, they are home to 85% of the world's vertebrate species. So warming on mountains and how climate affects biodiversity in mountains is going to have huge implications for the future of a large fraction of terrestrial biodiversity. And so this is especially concerning. The Himalayas are a very interesting system. The Himalayas formed about 45 million years ago when the Indian plate hit the Eurasian plate, causing uplift of these mountain ranges, the tallest mountain range on Earth. And they show strong abiotic and biotic gradients. So if we go from, this is a map of pretty much the Himalayas. And what you're seeing is India, Nepal, and Bhutan, Nepal there, and Bhutan there, and the rest of the Himalayas is India. What you're seeing is very strong abiotic and biotic gradients in the Himalayas. So if you look at annual variation in temperature, for instance, you look at annual temperature variability in the east at a point there versus the west, what you're seeing is that the west is twice as seasonal in terms of temperature variation as the east. So temperature fluctuates between summer and winter twice as much in the west than it does in the east. You also see a very strong biotic gradient from west to east, which is in the number of bird species. So the east has roughly twice the number of bird species in the, as the west. So you see this very, very strong biotic and abiotic gradients that allow us to really test whether it's temperature or competition that is setting elevational range limits for these bird species. You would expect, if Darwin was right, then temperature would be setting range limits in the west, because the west is far more seasonal than the east, and competition would be setting range limits in the east because the east has twice the number of bird species that the west has. So if Darwin is right, temperature is setting range limits in the west, competition is setting range limits in the east. So what we did was to go to these two locations, 1,500 kilometers apart. In the west, the Great Himalayan National Park, and in the east, the Eaglenest Wildlife Sanctuary, and set up transects that spanned a roughly 2,000 meter elevational gradient. So we had multiple transects spanning from, in the east, from 1,000 meters to 3,000 meters, in the west from about 1,750 meters to 3,500 meters above sea level. And on these transects, what we did was place these automated temperature recorders called thermochrons at regular intervals on these transects. So if I had a transect that goes, in this case, I have a transect that goes from, let's say, 1,000 meters, 1,500 meters. There are 5 of these temperature loggers spaced apart evenly. And they're taking in situ temperature measurements while we are actually walking these transects and recording birds. So if I see a fire-tailed Myzornis at this location X, I can tell you what the minimum and the maximum temperatures were on that day when I saw that bird, based on these 2 temperature measurements from the loggers on either side of it. So for every bird record that we have on these transects, we have a daily, for that day, the minimum and maximum temperatures that were recorded for that location. And what we did was to do this in summer and in winter. And the reason for that is 70% of Himalayan birds are altitudinal migrants. So most of these species breed higher up in the summer and winter lower down. So they're breeding at high elevations. And then when it gets very cold higher up, they're actually moving down to lower elevations. So we did this, walked these transects in summer and winter, measured the daily temperatures for each species separately in summer and separately in winter. And what we did then was to look at, in this temperature space where you have minimum temperature on the x-axis and maximum temperature on the y-axis, we look at what the temperature space occupied by the species in summer is, what the temperature space occupied by the species in winter is. So that's C, that space is C for summer and D for winter, and then look at the overlap between temperatures occupied in summer and winter. So if the species was perfectly thermally specialist and the species was absolutely adapted to one particular thermal niche, then C and D would overlap perfectly, as in the species would move between summer and winter such that it would occupy the same thermal niche space in both summer and winter. So we quantify what the overlap between the niche space in summer and winter is, and that's that niche space, but corrected, because the Western Himalayas and the Eastern Himalayas have very different thermal profiles in general. And that would be, for instance, what is the summer temperature range available in the Eastern Himalayas? That's A. What is the winter thermal space available in the Eastern Himalayas? That's B. And so we correct for, at every location, we correct for the overall available thermal thermal space. So it's not just a simple C intersection D, but it's then corrected by the available overall available thermal niche space in each location. So we do that separately for the Eastern Himalayas and separately for the Western Himalayas. And what we find, if you look at body mass on the x-axis and you look at thermal niche overlap on the y-axis, between summer and winter, that is. So what is the overlap degree to which thermal niches are overlapping between summer and winter? We find that small species seem to be poor thermoregulators. So as the smaller species on the left end of this graph have much higher seasonal thermal niche overlaps than larger species, which makes sense because small species are likely to be poor thermoregulators, whereas larger species, just by virtue of their size, should be able to deal with more extremes in temperatures easier than smaller species do. But this relationship between mass and thermal niche overlap across seasons is far stronger in the Eastern Himalayas than it is in the Western Himalayas. So that slope in the Eastern Himalayas is twice the slope that you see in the West, which indicates that Eastern communities as a whole seem to be more thermally sensitive than Western communities are. But it's not just about communities as a whole, it's also about populations of the same species in the East and the West. So if you look at 10 species that are found both in the Eastern Himalayas as well as the Western Himalayas, the Eastern Himalayan populations of species show far higher thermal niche overlaps even after correcting for available thermal space. So the seasonal thermal niche overlap for these 10 species, the populations in the East have far higher seasonal thermal niche overlaps than populations in the West. And populations in the east are represented by the green dots, populations in the west are represented by the brown dots, which seems to indicate that even within a species, populations in the east are far more thermally sensitive than populations in the west, in that populations in the east probably have adapted to be thermal specialists because of the low inherent seasonality, whereas populations in the west, because of the higher seasonality, might have adapted to become thermal generalists. So even within a species, you see these very interesting differences between two locations that are either very, very seasonal or not very seasonal at all. So it seems like species and populations in the relatively aseasonal eastern Himalayas are thermally constrained. And that is a problem because there are a lot of bird species in the eastern Himalayas, a lot of species in general in the eastern Himalayas. The eastern Himalayas actually is globally second in terms of biodiversity after the Amazon Andes gradient. And if they are this thermally specialized and warming is occurring 3 times the rate of the global average, then these species will need to do a lot of catching up to deal with the impacts of climate change. When it comes to, excuse me, when it comes to habitat loss and degradation, where what we studied is logging, selective logging, and how that impacts the survival rates of Himalayan birds. This is an aerial photograph showing you selectively logged forests on the left and primary forest on the right. So you look at the right, you basically got a closed canopy. You look at the left, you have an open canopy because some of the tree species have been removed from this forest patch on the left. So selective logging is the practice by which a subset of commercially important forest trees are removed from the forest. So it's not as drastic as outright habitat loss, where you clear the forest for agriculture, for instance, but it still does have impacts on forest structure. So you can see on the left that the forest canopy is open. There are trails that have been opened up in that forest patch for the removal of trees, and that does have abiotic and biotic impacts on communities and forests. We're interested in birds, so we looked at the abiotic and impacts in terms of temperature and humidity, which is on the left there. And you can see that the average temperature is about 1 degree Celsius higher in at warmest time of day. A log forest, which is in brown, has about a 1 degree Celsius higher temperature than primary forest. But the maximum temperatures in log forests are 6 degrees higher than they are in primary forest, which is a huge jump in temperatures. The difference between 18 degrees Celsius and 24 degrees Celsius is massive. And it's expected to have massive implications for how species thermoregulate and for bird and their prey communities in general. Relative humidity, which is below the temperature graph there, which is B, is uniformly lower in logged forest in brown than it is in primary forest. And this is especially likely to have impacts on species that are ectotherms, like arthropods. And arthropods are very, very important prey for most of the bird species that we study. And we do see that happening. We do see changes in arthropod communities between primary and log forest. On the right is an MDS graph showing you the composition of multiple arthropod samples in primary forest represented by green and log forest represented by brown. And you can see that the overall composition of arthropod communities in log versus primary forest are quite different from each other. A lot of the orders that these birds rely on for their diets, like Hemiptera, bugs, arachnids, spiders, and Lepidopteran larvae, butterfly and moth larvae, caterpillars, basically, are far more abundant in primary forest. Whereas for one particular guild of birds, which are flycatchers that feed on dipterans or flies, dipterans are far more abundant, far more common in log forest than they are in primary forest, which makes sense because you've got all this sunlight filtering in with an open canopy in log forest. So you do see both changes in the abiotic environment for these birds in terms of temperature and humidity, and you do see changes in the biotic environment for these birds, which is differences in the availability of prey. But the question is, are these populations in log forest viable at all? And typically what people do, what we have done as a scientific community is to study, when you say, what happens with logging, we typically tend to look at things like species richness, things like community composition of birds. But the mechanism that actually drives all of this is our demographic vital traits like survival and recruitment. So survival and recruitment determine population growth rate, which then determines the abundance of birds. The abundance then determines whether a bird is present or absent at a particular location. And summed across all species, the presence determines species richness. So what we were really interested in is understanding these demographic vital traits that underpin those larger patterns in species richness. What we did was work in Eaglenest Wildlife Sanctuary, which is in the eastern Himalayas, and work in cloud forest at 2,000 meters above sea level. This is very humid, wet kind of forest, and it's been logged. The primary forest has about 200 trees per hectare. That's the density of trees in primary forest, whereas the log forest has about 75 trees per hectare. So there's a drastic reduction in the tree densities in these log forest plots. And you can see the differences in the structure where you have a relatively close canopy on the left in the primary forest and very low understory vegetation densities. Which go to log forest, the canopy opens up. There's all this sunlight filtering down into the understory, leading to the proliferation primarily of bamboo in the understory. So there's huge structural changes between primary and selectively log forest. And we've been monitoring 3 plots each in primary and log forest. The primary forest plots are outlined in green and the log forest plots are outlined in red. And we've been doing this since 2011 using mist netting and bird ringing. So each of those white spots is the location of a mist net. And what we do is we go in year after year to the same plots, the same locations in the breeding season, put out those mist nets, net for 3 days consecutively in one plot, and then move on to the next plot. So it takes a total of 18 days of mist netting to be able to cover these 3 plots in primary and in log forest. What is mist netting and ringing? Mist nets are basically near invisible nets that are placed in the forest. Our nets are 12 meters wide and about 2.5 meters high. They have 4 shelves. They're actually quite invisible, even though I know where my nets are. I've walked into them on multiple occasions. So I can't I can't see them. Sometimes birds certainly can't see them against transparent against background of vegetation, and so they fly into them. They get caught. We remove the bird from the net. Ring it with a numbered aluminium ring so that we can identify individuals, then go back year after year to the same locations and put out the nets there again and see, based on the number of captures we're getting, fresh captures of birds that have not been ringed in the past versus the number of recaptures we're getting. We're able to tell, estimate things like survival rates. Now, from our netting, we know that bird communities are different in primary and log forest. Again, primary forest, this is an NMDS, primary forest in green and log forest in brown. And bird communities are different between primary and log forest, but what we're really interested in is understanding the mechanisms underlying those differences, the demographic mechanisms underlying. So what is at least more interesting to me is understanding things like survival and fecundity and recruitment. What we get from mist netting by being able to identify individuals are what are called capture histories. And this is an example of a capture history over 3 years. So ones indicate that the species was captured in a particular year. Zeros indicate that the species was not captured in that particular year. So if you look at the individual at the bottom, Z43096, that's his ring number. It was captured in year 1. It was not captured in year 2, but it's captured in year 3. And we've done this over the last 11 years. And the process that generates these capture histories are two probabilities. The probability that the bird survives from one year to the next and remains in the same location, which is typically denoted by the Greek letter phi, and the probability that the bird is captured, which is the capture probability, which is denoted by P. And so each of these capture histories is generated by a certain formulation of P, capture history, and phi, which is survival rates. And so, for Z43096, we know that the bird survived from year 1 to year 3. So it was captured with some probability P1 in year 1. It was not captured in year 2, but it survived from year 1 to year 2. And then it was captured in year 3. And it survived with some probability phi 2 from year 2 to year 3. So based on all of this, we're able to estimate survival rates of birds. And over the years, we've had about 9,300 captures of 4,300 individuals across 135 species in these 6 plots. You can imagine how biodiverse this area. This is just one elevation in the Himalayas, and it's just understory birds. So we're not catching anything that's up there in the canopy. So it's an immensely biodiverse location globally. But even though we captured 135 species, market capture analyses are very data hungry, and we're able to estimate the survival rates of only 20 species that are represented by these 3,310 individuals. And we wanted to compare these survival rates in logged and primary forest. One of the very important life history traits or behavioral traits of forest birds globally is mixed species flocking. And you have a bunch of species that are mixed species flockers versus a bunch of species that are marked by the crosses, which forage solitarily. And mixed species bird flocks are these very, very cohesive networks of species associations. These are species that, unlike single species flocks, these are multi-species groups that forage and move together. And you will find the same species associating with each other very, very consistently. And we know that the mixed species flocking phenomenon provides a lot of foraging benefits for the participants in the flock, and provides anti-predator benefits. So early warning, for example, against predation. So both foraging and anti-predator benefits are directly linked to survival. And so you would imagine that species that are able to join mixed species flocks and vary the composition of these mixed species flocks in response to changes in resource availability and predation rates in log forest might be able to maintain survival rates in selectively logged forests, whereas solitary foragers that don't have, it's just not hardwired to be able to join other species might show declines in survival rates. And that's exactly what we find. So you have on the x-axis 2 different kinds of species that join mixed species flocks, species that don't join mixed species flocks. The green bars are primary forest, the brown bars are log forest, and the y-axis is survival rate. And there's no evidence that survival rates are different between primary and log forests for the species that join mixed species flocks. And we know that actually the mixed species flock compositions are subtly different between primary and log forests. And we think what is going on is that these species are able to, well, not consciously, of course, but these species are varying flock compositions between primary and log forests to be able to overcome changes in prey availability and changes in predation pressure. Whereas if you look at solitary species, survival rates actually drop by 30%. So solitary species are actually facing survival declines in logged versus primary forest. The other trait that we were interested in looking at was whether species are residents versus whether they're elevational migrants. You've got a bunch of species that are resident. They stay in the same location, in the same home ranges in summer and in winter. And a number of species with the tick marks that are elevational migrants. They breed higher up and they winter lower down. Does elevational migration confer any kind of survival benefits for these species? We found a small effect where elevational migrants seem to have, there's no evidence that survival rates are particularly different between primary and log forest for elevational migrants, but residents seem to show a very small 10% decline in survival rates in log forest compared to primary forest. So it seems like it's the solitary resident species that are facing the greatest threats from selective logging or from land use change. Finally, when we're interested in looking at the interactive impacts of climate and forest loss. So none of these species are facing climate change and habitat degradation in isolation. They're facing both these threats together. So we need to understand how they're going to respond to a combination of climate change as well as habitat loss. So you've got climate change that is altering the natural temperature gradient across elevation. So there is a natural gradient in temperatures with elevation. As you go higher up, temperatures come down, and that entire gradient is shifting upwards because of climate change. And superimposed on that is the land use change abiotic gradient. Land use change is causing temperatures to go up, humidity to come down. In log forest, for instance, like I was saying, the maximum temperature is 6 degrees higher than in primary forest in our system. Agricultural lands can actually be at their hottest 13 degrees hotter than primary forest, and they're much colder at night because the buffering effect of the canopy is lost. So not only do you have this natural gradient in temperature shifting upwards because of climate change, superimposed on that, you have this land use gradient that is causing changes in the abiotic environment. Again, what we're looking at is selective logging as the land use change component at this 2000-meter elevation. And what we're looking at on those same plots, 3 plots in primary forest and 3 plots in log forest, is survival trends over time. Survival trends over time caused by the movement of species because of climate change. So we are sampling at 2000 meters, and given that different species have different elevational ranges, we're either sampling close to the cold edge of a species elevational range. For instance, this white-tailed robin, which has the bulk of its elevational range below 2000 meters, we're actually sampling near the cold edge of its elevational range. And you have other species that are primarily higher elevation species, and we're sampling near the lower edge of this species elevational range, or sampling closer to the warm edge of the species elevational range. And we expect that because species are going to be moving upwards, upslope, shifting their elevational ranges upwards because of climate change, that survival rates at 2000 meters, where we happen to be sampling, are going to change differently for these two types of species. So we should see survival increases for the low elevation species, because earlier we were sampling at the cold edge of the species elevational range, but as the species moves up in response to climate change, 2000 meters should become more and more favorable for this species as an abiotic environment, and therefore over time survival rates for these low elevation species should increase as it moves up, with 2000 meters being more and more suitable for it. Whereas this high elevation species, where we're sampling close to the warm edge, it's leaving 2000 meters to go higher up. 2000 meters is becoming more and more unsuitable for this species to survive in, and therefore we should see survival declines for species that are higher elevation species. We're able to estimate survival trends for 15 species represented by 2,500 individuals, and we've done this for 2011 to 2018. What we see in primary forest is this. We see a lot of species that have, again, x-axis is time, y-axis is survival rates. We see that species are showing, some species are showing massive declines in survival rate over time in primary forest. Some species like F and G and E are actually not showing too much change in survival rate over time, whereas some species are showing actually survival increases over time in primary forest. For some species, we just didn't have enough to estimate survival rates in primary forest, but we were able to do that, estimate the survival rates in log forest. So you see this heterogeneity in survival rates, changes in survival rates over time in primary forest. And is that explained by the elevational ranges of these species? Just to remind you, we're sampling at 2000 meters. So species that have the midpoint of their elevational range below 2000 meters are pretty much low elevation species. Species that have the midpoint of their elevational range higher than 2000 meters are higher elevation species. And so you've got low elevation species there towards the left, and those species should be showing increases in survival rates over time, right? So the y-axis is the slope of survival over time. If the slope is positive, then survival is increasing with time. And the species that are higher elevation species that have the midpoint of their elevation range greater than 2000 meters should be showing declines in survival rates over time. So the slope of survival over time should be negative for these species. We do actually see that. We do actually see in primary forest that there is a negative relationship between the midpoint of a species elevational range and its survival trends over time, where in primary forest, low elevation species are showing increase in survival over time, whereas higher elevation species are showing declines in survival over time, which is consistent with elevational range shifts of these species because of climate change. But strangely, in log forest, we don't see that happening. Pretty much in log forest, survival rates are remaining constant over time. And so if you look at the slope of survival over time for these species in log forest, it's not really explained by the midpoint of a species elevational range. It's not explained by the elevational range of a species. And what does actually explain the heterogeneity in survival rates of species in log forest and how survival rates of species in log forest changes over time? Turns out it's probably niche overlaps between populations in primary forests and populations in log forests. So if you measure the temperature and the humidity of every bird capture, so we put out a mistnet, and associated with the mistnet is a data logger that's collecting at every 10-minute intervals temperature and humidity readings. And so for every capture that we get of a bird, we know what associated temperature and the humidity was for that individual. And if you look at the temperatures and humidity space occupied by populations of the same species in primary forest represented by green and log forest represented by brown, you can calculate the overlap between temperature and humidity, the abiotic niche space occupied by a population in primary versus log forest. And so if a species has very high overlaps between primary and log forest, then it's able to find the same niche that it occupies in primary forest in log forest. Whereas if you have a species that has a completely different abiotic niche in log forest, very little overlap between primary and log forest abiotic niches, then that particular species is unable to find the kind of habitats that it prefers in primary forest, kind of abiotic habitat that it prefers in primary forest. It turns out that this is very, very strongly related to how survival changes over time in log forest. So the x-axis is niche overlap between primary and log forest, and the y-axis is the slope of survival over time. Negative values on the y-axis represent declines in survival. Positive values on the y-axis represent increase in survival. Low values on the x-axis represent a species that has very, very different abiotic niche in primary versus log forest. So what we're seeing is that species that have those very, very low values of niche overlap in primary and log forest, species that seem to not be able to find the kind of abiotic environment that they prefer as a baseline, are showing huge declines in survival over time. Whereas species that have higher overlaps in their abiotic niches in primary and log forest actually are able to maintain their survival over time. Other interesting patterns we're seeing is that all of these species are actually showing body mass declines in log forest, but maintaining body mass in primary forest. So the y-axis is the slope of mass over time. So negative values means that body mass is declining over time. And zero means that body mass is not changing over time. So that's the slope of body mass over time. And in log forest, most species are showing declines in body mass that seem to be becoming smaller and smaller over time, which again, these are preliminary results that we're looking into, planning to investigate things like thermal stress in primary versus log forest and how that differs between these two different kinds of habitats, what implications that has for survival. But it does make sense that as the habitat becomes hotter and hotter, and log forest is much warmer than primary forest, the body masses should become smaller because smaller individuals are better at losing heat than larger individuals would be. So in effect, what happens between log forests and primary forests is that the abiotic niches do change with logging. Logging seems to be selecting for species that are climatically adaptable, the thermal generalists. And climate logging synergies reduce survival rates. And this is important, very, very important, I think, because we need to be factoring climate impacts into land use studies. So if I just looked at overall average survival rates for the white-tailed robin, for instance, which is the panel with the box plots there, I look at the average survival rates and I would come to the conclusion that there is really no evidence to say that survival rates are different between primary and log forest. But if I look at the trends on survival over time, I see drastic differences between these two. So I'm actually seeing that this species moving into 2000 meters from below is able to increase survival rates or maintain survival rates far better in primary forest than it is able to maintain survival rates in log forest. So the rate at which survival increases over time in primary forest is far higher than it is in log forest. And snapshot studies that just say, I went in here for a 2-year period and I compared what happens is, let's say, survival rates, so community composition between two different kinds of habitats. And you come to some conclusion that there is this difference. But you go 10 years later, climate change might have caused a complete reversal of those patterns. So land use studies really need to be cognizant of the fact that we're on that climate spectrum somewhere, we're on that climate change spectrum somewhere. And the patterns that you see comparing 2 or 3 different land use types might change quite drastically 10 years or 20 years from now because of climate impacts. But the take home here seems to be that for species to be able to adapt to climate change, we need primary forest at all elevations. We need continuous gradients of primary forest across elevation so that when species move upwards, they're able to occupy primary forest and they don't end up in, say, agriculture or selectively log forest or other forms of land use change, which basically reduces their ability to cope with climate change, reduces their ability to adapt to climate change via range shifts. What we've done using these results is consulted with the tribal community that administers this land. This is the community called the Bugun community. They are a village of about 70 households, and they administer de facto. They own and manage 90 square kilometers of land in this area, land that is home to an extremely critically endangered bird species, probably one of the rarest bird species in the world, called the Bugun leochicla. The Bugun leochicla has a population not exceeding, a known population at least, not exceeding 20 individuals. So it's phenomenally rare. And the global range size of this species is 2 square kilometers. So not only is it inherently rare in terms of population size, it's got a low population size, but it's also got a very, very small geographic range. So it's vulnerable to both demographic stochasticity as well as environmental stochasticity. It's the worst form of rarity possible for the species. And the entire range of the species is on the lands of Singchung villages, community forests. So we've been working with the Singchung village and the Arunachal Pradesh Forest Department to sort of try and have this land protected and protect as large of an elevational gradient as possible on these lands to allow species to be adaptable to climate change. And very hearteningly, the community, the Bugun community of Singchung village, voluntarily declared 17 square kilometers of their land as the Singchung Bugun Village Community Reserve in 2017. And they are planning to expand this community reserve by an additional 30 square kilometers. That 30 square kilometers here spanning 1,200 meters above sea level to 3,200 meters above sea level. And so that protects effectively a 2,000-meter elevational gradient that then allows species to potentially be resilient to the impacts of climate. And therefore, trying to ensure that, at least in this one location, climate change and forest degradation are sort of mitigated to some extent, and the future of Himalayan biodiversity in that one little spot is brighter than it might be. So I'll end here. Thank you very much. Thank you very much for hosting me. Thank you very much for giving me this opportunity, and I'm happy to take questions.